Hello everyone. Today your class number 8. Today is class number 8 for EMFT. Okay. So for this case, up to this much I have discussed that the divergence concept, curl concept, gradient concept, and then vector integral concept, that is Stokes theorem, Green's theorem, that is Gauss's divergence theorem. So today I will discuss the Green's identity. Okay, so next topic is Green's identity. So please write Green's identity. Green's identity. So what is the Green's identity? Actually, Green see that any two scalar can form a vector. That any two scalar, the physical concept of any two scalar, if we add up by some exactly some important fashion, that is some importance fashion, then it will form a vector quantity. So here before start the Green's identity, I will discuss that any vector, suppose A is a vector. Okay, suppose A is a vector which can form by two scalar components, that is phi and psi. Suppose this phi and psi are two scalar components, it is function of phi and psi. Suppose A vector is a function of phi and psi. Okay, so these two vector, this vector and these two scalar component can be related as a, suppose let us assume a vector A, or let us assume a vector equals to, let us assume vector A equals to phi grad psi. Pronunciation will be phi grad psi. This is a gradient of psi. Okay, so gradient of psi means a vector, and this vector multiplied with the scalar produces vector. See, it is a scalar, right? This term is a vector, right? And multiplied with these two is another vector. Okay, so a vector, this vector can found by multiplying these two scalar components, or a exactly particular fashion of the relation between them will be this way, and we will be form a vector A. Okay, so apply here, right? Apply divergence theorem. Over a vector. Apply divergence theorem over a vector. So what is the divergence theorem? So we are taking right hand side here, so no problem. So right hand side, that is divergence of this vector, that is phi grad psi, which will be equals to closed surface integration phi grad psi into ds vector, right? Dot ds vector. Okay, this is the expression. Just we put this a vector, value of this a vector over here. Okay, so now what is the concept? See, this is one important identity. This is one important identity. Divergence of this one and this one consists of a gradient. Okay, so what happened? It will be looks like divergence of AB. So A, taking A as common, divergence of B, plus B taking B as common, divergence of A. Okay, so if A is a vector, then it will be divergence. If A will be scalar, then it will be become, or B will be scalar, then it will become gradient. See, if we see this A dot B, so this A is a scalar, right? So we can pronounce it as a gradient of A, grad of A. Okay, and if B is a vector, suppose B is a vector, okay, or AB are two vectors, then we can pronounce that by this way. It will be then divergence of A. Okay, so here it will be gradient of A, as A is not a vector, A is a scalar quantity. So here it is a scalar, it is a vector, right? So if we apply over here this concept, then what happened? Triple integration of taking this one as common, okay, grad of psi taking outside and grad of phi over here, okay, plus phi taking outside as a common and grad of divergence of psi, okay, grad of divergence of psi. So if we break it into two parts, then once this is your A, this is your B, right? So A is a scalar, B is a vector. See, A is a scalar and B itself is a vector. As this is a B, this is your A into B, and this is your A, or this is your psi actually. So this is your A dot B vector, right? So this is your A, B. So A means what? Phi. So phi taking outside here, and B will be diverged, and here B will taking outside and A will be diverged. So that's why we pronounce it as a gradient of phi, and here we pronounce it as a divergence of gradient of psi. Okay, so if we expand it, so it will come. Okay, so next right hand side will be what? Right hand side suppose remains same. Right hand side remains same. Okay, right here same thing remains same. Okay, see here we can see that this is the Laplacian, right? Divergence of gradient means what? Divergence of gradient means Laplacian. So next line please write Laplacian of psi equals to this right hand side part, equals to this right hand side part. Okay, so just I am, this one is my Laplacian as this one. Okay, nothing else. Okay, make it equation number 1. Make it equation number 1. So now just replace, now right, replace phi and psi each other. That is swapping. We are swapping phi and psi. Then what happened? Then your result will be from equation 1. So if we compute this equation directly by swapping these two, then we have divergence of psi, it will be phi dot divergence of phi, it will be psi, then plus phi, here it will be psi, and Laplacian of psi, it will be phi, right? So this one equals to, here it will be phi, sorry, here it will be what? Here it was phi grad psi, right? So here it will be psi grad phi double integration closely over ds. Okay, make it equation number 2. So now from the equation 1 and 2 just subtract themselves. Subtracting equation 1 and 2. So what will be your answer? Subtracting equation 1 and 2. By subtracting equation 1 and 2, you have, see, this term is cancelled out from each equations. Why? Because divergence of phi multiplied with divergence of psi, and similarly the previous one has divergence of psi into divergence of phi, same thing. So they are, if we subtract themselves, if we subtract 1 minus 2, okay, then what happens? So 1 minus 2 will results as double integration phi Laplacian of psi minus psi Laplacian of phi, psi Laplacian of phi, okay, which will be equals to over dv, which will be equals to closed surface integration phi grad psi minus psi grad phi. okay, over ds. So this is your Green's identity. So in case of your semester exam, suppose this type of question has to be asked very much, that find the Green's identity, then you have to compute these all terms and find this final expression. Okay, this is your Green's identity. Okay, so the first module, last chapter will be your Helmholtz theorem. So last topic is Helmholtz theorem. Helmholtz theorem. So what is Helmholtz does? Helmholtz did that, right, a vector field is uniquely described, any vector field, right, any vector field is uniquely described within a region by its divergence and its curl. That means any vector field is can be uniquely described within a region by its divergence and the curl. Okay, so next write, continue. If the divergence and the curl of any vector f are given as, if the divergence and the curl of any vector capital F are given as divergence of f, suppose we are taking f vector over here, okay, equals to rho v vector, and curl of f vector equals to, sorry, divergence of it results scalar, right, so it will be scalar value and it will be vector. Okay, so see what happened. Suppose any vector, suppose this room containing a vector f. Okay, so this vector has two types of effect. What are the effects? Someone is diverging and second one is rotating. First one is diverging in nature, so forces can be diverging. So what do you mean by diverging? So total energy, can we write total energy of F equals to total energy of F equals to inside energy plus outside energy. That is inside energy and redundant energy. Inside energy means redundant energy and outside energy means output energy from this system. So this system, the fluxes are coming out, okay, like this way. So this is the energy is coming out, okay, this energy is coming out. See, we are taking it as a outside energy, from outside energy from a vector, okay. And inside energy means what? Inside energy means the remaining part or redundant part of the energy inside this room. Okay, if we consider there is no energy is absorbed by this boundary, always remember Helmholtz theorem. Therefore, the Helmholtz theorem, you have to consider that there is no boundary condition. Okay, so boundary condition means, that means provided there is no energy is absorbed inside over the boundary of the system. Okay, so F is a vector which shows a energy system, and this energy can be expressed as by adding these two terms, that the inside redundant energy adding with outside energy from F. Okay, so here similarly this term divergence of F means what? The outside energy from F vector, and this one is the redundant inside energy. That means any vector can be expressed by these two way, or by this uniquely described by these two. Okay, so right here, according to Helmholtz theorem, F equals to F vector can be written as rho v plus rho s, right? Rho v plus rho s. So rho v means what? Divergence of F plus curl of f. Okay, once I am again conclude that this f and this f is not same. Why? Because suppose this f vector equals to 100 unit. Okay, suppose modulus of f vector equals to 100 unit. Okay, so 70 unit is coming outside, so 70 unit is the output and the remaining 30 unit are the redundant input. Okay, redundant part of the system. So can we express these at f and f? See, we cannot express. So from the base first one, please mention it will be f1 and f2. Then this is f1 and f2. From the basic, from the very first, please write f1 and f2 over here. Okay, so this f1 and f2 is nothing but two parts of this vector f. Okay, so write f1 equals to the part of f vector which produces a divergence field, divergent field, and f2 vector equals to nothing but part of f which produces a rotational field. See, rotational field always inside thing or inner part thing, and divergence is always outside part thing. Okay, so here after applying the Helmholtz theorem, any vector can be expressed by this way. Okay, so this f1 and f2 nothing but two parts of a complete vector. Okay, so this is your Helmholtz theorem. So proof of your Helmholtz theorem is no need to do. And now next topic will be, that means next thing I will move to the module 2. Okay, so today's class up to this much, and this module here this module is complete. And from after completing all modules, I am again start from very first, that is some important problems regarding of each module will discuss. Okay, or will be discussed. So please wait, and here the theoretical expression of each module, it is the completion of first module will be here, and the second module will start from next day. Okay, so thank you. Today's class up to this much.